Thank you for the introduction, and thank you to the organizers for the invitation. It's my pleasure to be here. I'm going to present isogeny-based cryptography and how it looks now after the snap. Is the sound okay? Yeah, perfect. So what I'm calling the snap, well, I'm sure most of you already know what that is referring to, but if you don't, I hope you're going to learn about it today. I'm going to start with, okay, so that doesn't work. It's on. Okay, I'm just going to use the computer. That doesn't work too. Maybe now that works. I'm going to start with an introduction to isogeny-based cryptography because I don't want to assume that everyone here knows about this field. I'm going to talk about elliptic curves, isogenies, the computational problems we're interested in. So first, elliptic curves. This, I'm sure, a lot of you are to some extent familiar with elliptic curves. They've been a classic object in cryptography for quite a while now. So we're working with elliptic curves over a finite field. Here my finite field is fq, and an elliptic curve is the set of solutions of an equation of that form, y squared is x cubed plus ax plus b. And they've been a very useful object, mostly due to the fact that they define an abelian group, which is typically written additively. Now, isogenies are simply maps between elliptic curves. If you have two elliptic curves, E1 and E2, an isogeny sends points from the first curve onto the second curve. And you don't want just any map. As I mentioned, an elliptic curve is a group, and you want these maps to preserve the group structure. So isogenies are group homomorphisms. There are more than that, but just knowing that there are group homomorphisms will be sufficient for the purpose of this talk. Also, they always have a finite kernel, which sounds trivial if I'm saying that we're working over a finite field, we expect everything to be finite. When I said it has finite kernel, I mean that even if you're looking at solutions of this equation over the algebraic closure, which is infinite, the kernel is still finite. And this number, we call it the degree. The degree of an isogeny is the size of the kernel. It measures how complicated the isogeny is. Degree 1 means it's just an isomorphism, and the higher degree, the more complicated it is, the more complex it is to compute the corresponding isogeny. And the degree behaves very well with respect to composition. The degree of the composition of two isogenies is just the product of the degrees. If you're thinking about all these objects, just in terms of group theory, this is a fairly natural property to have. So now with these objects, we can very naturally define a computational problem, which is the isogeny problem. Suppose you're given two elliptic curves. Can you find an isogeny between them? And now in isogeny-based cryptography, our goal is to define cryptosystems that are based on the isogeny problem in a sense. So based on the isogeny problem means, here's the expectation. You would like to design cryptosystems whose security is equivalent to the isogeny problem. And now the isogeny problem, we suspect it's hard. We suspect it's hard even for quantum algorithms. Therefore, we get post-quantum security. So before I go a little bit deeper in this direction of building cryptosystems, I want to say a little bit more about the isogeny problem. Is it really a well-defined problem? The input of the problem are two elliptic curves. It's fairly easy to describe an elliptic curve. It's just given by a polynomial equation. Give me the parameters that describes the elliptic curve. But now what does it mean to find an isogeny? How does it look like? How do you return an isogeny? An isogeny is a map. How can you describe it? A first hint in that direction is that the kernel of an isogeny, as I said, it's always something finite, it fully determines the isogeny, at least up to isomorphism. We're going to work only up to isomorphism here. Consider isomorphisms are trivial. So maybe to describe an isogeny, you can just give its kernel. And this is the first solution. Given the kernel of an isogeny, which is just a list of points, a finite list of points, then we can evaluate the isogeny in polynomial time, meaning for any input, we can compute the image. This is thanks to Velu's formula. And it works very well for isogenies of small degree. As you can imagine, it's not going to work so well for isogenies of large degree, because the degree is the size of the kernel, so the size of this list. So you want to use this method to represent isogenies of degree 2, maybe, or degree 3. Is that already enough? Well, the problem is that there are very few small degree isogenies. And in the isogeny problem, I give you two elliptic curves, and I'm asking you to return an isogeny between them. But typically, the smallest degree isogeny that's going to exist will have degree polynomial in P. P is the characteristic of my field. And in cryptography, most of the time, you're going to think about p larger than 2 to the 256. So you cannot represent a kernel of that size by listing its points. However, what you can do is use these small degree isogenies as building blocks. You can compose them together to build larger degree isogenies. As the degree is multiplicative, as you compose maps, you can get fairly fast to large degree isogenies. So like that, you can represent an isogeny of smooth degree, smooth meaning that all the prime factors of the degree are small. And then you can decompose your isogeny as a composition like that and represent each factor by the first method. Okay, we can think about these compositions as paths in a graph. Fix a small prime L, typically L equals 2. That's the case that's most commonly talked about. And an isogeny of degree 2 or of degree L, we call it an L isogeny. And you can think about L isogenies as edges in a graph. So in your graph, the vertices are your elliptic curves, here E1 and E2, and your isogenies are L isogenies that connect them. So it would be a directed edge a priori here. This is just part of a larger graph. Maybe from E2 you have other L isogenies that go elsewhere, maybe to E3 and E4. Then I want to point out here that when you have an isogeny from, say, E1 to E2, then you also have an isogeny of the same degree in the opposite direction. So you can see these graphs as undirected graphs. As I said, this is just part of a larger graph. Maybe you can consider all the elliptic curves you're interested in and all the isogenies between them, and you would get something like that. What do I mean when I say elliptic curves we are interested in? Well, we often want to focus on some interesting family of elliptic curve. Interesting meaning that you're going to get something finite, something nice, regular, connected, whatever. What we do in isogeny-based cryptography is most of the time we look at what we call supersingular elliptic curves. I'm not going to define supersingular elliptic curves, but all you need to know is that I'm making this implicit assumption along the entire talk that everything is supersingular, whatever that means. And what's very nice is that when you focus on supersingular elliptic curves, the graph you get like that by considering at all your curves and all the L isogenies, what you get is connected, which is very non-trivial because you've restricted the isogenies you're looking at very strongly. Here, the edges are only isogenies of degree 2. Why would there always exist a path composed only of isogenies of degree 2? Well, this is a fairly deep theorem that says that it always exists. It's also L plus 1 regular. So it's in this example, L equals 2. So this is a 3 regular graph. You have a few kinks. You have self-loop. You have edges with multiplicities. These are fairly rare. So you have a connected graph, and you can ask the path-finding question in this graph, which is the L isogeny graph problem, the L isogeny path problem. You're given 2 elliptic curves. Can you find a path in this graph? And this is really a path-finding problem in a graph, and it's believed to be hard. In fact, it's believed to be as hard as the generic graph problem. The best algorithms we have to do that are generic graph algorithms, finding a path in a graph. And this is what we typically mean when we say the isogeny problem. This gives a concrete meaning to what it means to find an isogeny between E1 and E2. Back to isogeny-based cryptography, here was the expectation. You want to build crypto systems that are as secure as the isogeny problem is hard. The reality, of course, is a little bit messier. And the isogeny problem does serve as an upper bound on the hardness of breaking essentially all isogeny-based cryptography. So if you can solve the isogeny problem, you can break all isogeny-based cryptography. But it doesn't often also serve as a lower bound. It doesn't give us security proofs, guarantees that if the isogeny problem is hard, then the crypto systems are secure. What we have instead is a bunch of weird scheme-dependent variants of the isogeny problem. Here are a few examples. Let's start with a good example. So sometimes the isogeny problem does also serve as a lower bound. We can prove that that breaking the CGL hash function, or finding primitives of the CGL hash function for Charles Goren and Lauter, is equivalent to the isogeny problem. So here's a good example. Here's another one, maybe not as good, but pretty close. Ski sign. So ski sign is a digital signature scheme. It's constructed as an identification protocol turned into a signature scheme by the Fiat-Shamir heuristic. So we can talk about the properties of the identification protocol. And the soundness of ski sign is equivalent to a problem known as one endomorphism. So one endomorphism is a problem that sounds a bit different from the isogeny problem. Well, it's just not the same name, but we've expected it to be equivalent to the isogeny problem for quite a while, and there's ongoing work to show that it actually is. I hope it's going to get out soon. So still a good example. We suppose we are fairly close to the isogeny problem here. Let's get a little bit farther from the isogeny problem with Seaside. Seaside is a key exchange protocol. The key recovery for Seaside is equivalent to a problem known as vectorization. Vectorization is very similar to the discrete logarithm problem. In the discrete logarithm problem, you have an exponentiation, and your problem is finding the exponent. In the vectorization, you have a group action, and your problem is finding the group element that acted. And this is a fair bit easier than the isogeny problem, at least according to our current understanding of the problem. We have much better algorithms to solve vectorization than we do for the isogeny problem. Still, we believe it's hard. And then there's SIDH. So you may suspect that SIDH is a big player in the talk that I'm about to give. So I'm going to focus a little bit on it. So SIDH, it was introduced by Zhao and DeFeo at PQCrypto in 2011. It's an isogeny-based key exchange. It has been very popular. It has essentially sparked the field of isogeny-based cryptography. It wasn't the first isogeny-based scheme for sure, but it attracted a lot of interest into the field. It's reached its peak last year when it was selected by the NIST post-quantum cryptography call as an alternate finalist. And its security is equivalent to a problem called SSIT. SSIT stands for supersingular isogeny with torsion. So it's like the isogeny problem with some extra information known as torsion point information. So I need to say a little bit more about it and talk more in depth about SIDH. How does it work? I'm going to need to talk about quotients. Quotients of groups, well, quotients of elliptic curves, but if you're familiar already with quotients of groups, that's going to help quite a bit. Consider an elliptic curve E, and G a finite subgroup of the elliptic curve. As I said, if you have an isogeny, the kernel of the isogeny is always a finite subgroup. So you could ask, is any finite subgroup of the curve the kernel of some isogeny? And the answer is yes, by quotienting. You have your isogeny, you have your elliptic curve E, you have your group G, you can quotient by G, and that gives you an isogeny from E to E quotiented by G. This isogeny is unique in a precise sense. It's unique up to isomorphism, such that the kernel of the isogeny is G. So if I give you a finite subgroup of an elliptic curve, there is a unique isogeny of which it is the kernel. And of course, almost by definition, from the simplified definition I gave of the degree of phi is the size of this group. And if you are given this group in the form of a few generators, instead of just a full list of whatever's in the group, then you can compute the corresponding isogeny in time polynomial in the largest prime factor of the order. So if you have a group G of smooth order, all of its factors are small primes, then you can compute it efficiently. So let's get to the key exchange. Here's how SIDH works. You have Alice and Bob, they want to exchange a secret. They fix a reference elliptic curve E0 that's known by everyone. And let's say Alice goes first. She's going to pick a random subgroup G of E0. She's going to pick G to be of smooth order, just so everything is efficiently computable, because now she wants to compute the corresponding isogeny, so quotienting by G. And the target, E0 quotiented by G, she calls it EA, is going to be Alice's public curve, and she sends that to Bob. And Bob does the same thing now with another subgroup. Oh, okay, first maybe I want to represent a diagram for this isogeny. So you have the starting curve E0, it goes to the quotient by G, and we call this isogeny phi A. Now Bob does the same thing. With a random subgroup H, he computes the corresponding isogeny, calls the target EB, and sends EB to Alice. Now, what could Alice do? Alice has received the quotient of E0 by H, and she knows G. So maybe she can quotient further by G. And quotienting further by G would mean quotienting by the group generated by G and H. If you first quotient by H and then by G, you get to the quotient by the subgroup generated by G and H. written G plus H. And she calls that EAB. Now Bob can do the same thing using the curve Alice sent him. Alice sent E0 quotiented by G. Pointing like this doesn't serve any purpose because I don't see what I'm pointing at, but I'm doing it anyway. And Bob is using the quotient that Alice sent her and quotienting further by H, and he gets to the same curve because quotienting first by H then by G is the same as quotienting first by G then by H. Okay, and this is SIDH, at least in spirit. This doesn't actually work. Why? Because look at that. We are saying that Alice is taking the quotient by H and quotienting further by G. But G is not exactly a subgroup of EB, right? G is really a subgroup of E0. What is a subgroup of EB is the image of G through Bob's secret. So Alice, to compute that, would need to have a way to compute phi b of her secret subgroup. But neither Alice nor Bob knows both components here. Alice knows G and Bob knows phi b, who could compute the image of the subgroup. Bob would need to give to Alice the means to compute the image of her subgroup. And this is solved in SIDH by working with torsion subgroups. Fix an integer n and an elliptic curve E. A point is of n torsion if when you add this point to itself n times, you get 0. We call that multiplication by n, so n times p is p plus p plus p plus p is 0. The collection of all these points, we call it the n torsion subgroup. It actually is a subgroup, and we know very well its structure. It's always isomorphic to z mod nz squared. So here's an idea. Alice could pick her subgroup G, not as some arbitrary subgroup of the curve, but as a subgroup of the 2 to the n torsion. Why 2 to the n? Well, because first of all, she needs the subgroup to be of smooth order for it to be efficiently computable. So what's smoother than a power of 2? Not much, so it sounds like a good choice. Also, Alice needs a lot of freedom in her choice because it's going to be her secret. She needs to have a lot of entropy in her secret. And you have many subgroups of z mod 2 to the nz squared. So this gives her hope that her secret has enough entropy. Now Bob needs to give Alice the means to evaluate the image of G through his secret. So maybe he can reveal his secret isogeny restricted to the 2 to the n torsion. So just part of his secret. And we hope that this doesn't leak any information about what's happening with the isogeny outside the 2 to the n torsion. It doesn't really leak the full isogeny, just part of it, and the part that is interesting to Alice, because now that she knows the isogeny on the 2 to the n torsion, and her secret is part of the 2 to the n torsion, she can compute its image, and therefore she can compute the shared secret. Okay, so here's the updated protocol. I've added in red what's new compared to the idealized version I presented before. In the setup, they both need to agree on some basis of the 2 to the n torsion, which I write P2Q2. And giving the restriction of a secret isogeny on the 2 to the n torsion means giving the image of this basis. So here, Bob takes the basis of the 2 to the n torsion, so P2 and Q2, and reveals the images to Alice. The protocol needs to be symmetric between Alice and Bob, so Alice needs to also reveal some part of her secret to Bob, and she's going to do that with the 3 to the n torsion. So Bob chooses a subgroup of the 3 to the m torsion. Why 3 to the m? Because it cannot be the same part as Alice's. Why? Because Bob's secret isogeny, he's going to reveal its restriction to the 2 to the n torsion. So if he chooses a kernel that is in the 2 to the n torsion, revealing this part would leak the kernel, and the kernel determines the isogeny. So Bob uses an isogeny whose kernel is in the 3 to the m torsion. Then he can leak the restriction to the 2 to the n torsion without fear of revealing the kernel. And OK, so that explains why it's different from 2 to the n, and why 3? Well, because 3 is the next best thing after 2. And this is the SIDH protocol as it was proposed. So as you can see, it doesn't look quite like we are relying on the pure isogeny problem anymore. Before we added these red things, what was exchanged was only elliptic curves. So we had E0 and EA and EB as public values. And the secret of Alice was essentially the isogeny between E0 and EA. So recovering the secret would have been, I'm just given the two curves, can I find the isogeny? That is the isogeny problem. Now more information is revealed. And this leads to the SSIT problem. The SSIT problem is the following. You're given two curves, E0 and E1. You're given a basis PQ of, say, the 2 to the n torsion of E0. And you're given the images through phi of this basis PQ. Now, can you find the isogeny phi from E0 to E1? This red part here is what we call the torsion point information. If you remove it, it's just the isogeny problem. If you add it, it's the SSIT problem. And the security of SIDH is equivalent to the SSIT problem. So you expect this extra torsion point information to make your problem easier, because of course it's just more information. It's more you can work with to find the very same output. Has this ever been a concern? Have people suspected that this could be an easier problem than the pure isogeny problem? Well, of course, there's a history of attacks exploiting torsion point information. Here's a quick timeline. The birth of SIDH was in 2011. It took a few years until 2016, where the first active attack exploiting torsion point information was found by Galbraith, Petit, and Silva. Active attack means that the attacker needs to change the information that is exchanged between Alice and Bob. The attacker introduces errors in what is exchanged, and depending on how Alice and Bob react to this error, they can guess a few bits, and bit by bit, they can reconstruct the entire secret. The first passive attack came a year later when Petit showed how you could break some overstretched version of SSIT. Overstretched means that the amount of torsion information that is revealed is enormous, much bigger than what is actually revealed in SIDH. But he shows that if you have enough torsion point information, then you can break the SSIT problem. This was improved in 2020 by a few authors, where the improvement comes in reducing the amount of torsion point information that is required for the attack to work. Still far short from breaking actual SIDH parameters. The amount of torsion point information required there was still large. That is until the snap. So imagine it's July 2022. As the rest of Europe, you're enjoying your vacation here in the French Alps. Very pretty. It's my little advertisement for the French Alps. And then this was my last day of vacation, or almost the last day. And after that, I was in the car going back home. I wasn't driving. I was checking ePrint for updates. And I see this title, An Efficient Key Recovery Attack on SIDH. So, OK, what comes in your mind when you see that? Maybe probably just another crackpot paper. And then you check the authors and you think, OK, maybe they're onto something. And then you read the abstract. Is it really serious? Really, is it a full attack? Well, they say they break the Psych P434 challenge in 10 minutes. That is supposed to be NIST security level 1, 128 bits of security. So this doesn't smell good, right? So did they really break it? Well, yeah, they did. And this was the first of a short series of papers improving the attack. And here's what the Eurocrypt 2023 Isogeny 1 session looked like. It's pretty grim. Efficient key recovery attack on SIDH, the paper I just mentioned by Castric and Decru, which of course got the best paper award, followed by a direct key recovery attack on SIDH, and then breaking SIDH in polynomial time. So you may wonder, are these like, is that all the same paper, or what's the deal here? Well, they're essentially in chronological order, increasing order of sophistication, of range of applicability, of speed, implementation, whatever. They all have different improvements. The main message of these attacks is the following theorem, which you can extract by looking at all three papers. This is the main result, and it's something that we could absolutely not dream of more than a year ago. Suppose you have an isogeny phi from E1 to E2 of degree some integer d. And consider an integer n just large enough, larger than half the logarithm of d, so not too crazy. And consider a basis pq of the 2 to the n torsion of the source of your isogeny. The theorem says if you're given this tuple, you're given the degree, the basis PQ, and the image phi of P and phi of Q, then you have your isogeny. You can evaluate your isogeny on any other input. You can see that as some form of interpolation of isogenies. If you know your isogeny on a few points, then you know your isogeny everywhere. It's like polynomial interpolation. You have a degree D polynomial. If I give you D plus 1 distinct evaluations of this polynomial, then you can recover the polynomial. This is what's happening here. And an immediate corollary of that is that, well, the points that are revealed by the SIDH key exchange actually leak the full secret. OK, so that is the main result of the attack. I'm going to talk later about how it actually works. For the moment, let's run a body count. So what's out? Of course, SIDH is out. And with it, a lot of more or less inspired, SIDH-inspired protocols. So B-side is gone, KSIDH is gone, Shita is gone, Shields is gone. A lot of protocols that were a bit too close to SIDH for their own good. What about the rest? Well, it's not that bad. A lot of survivors. First, the isogeny path problem itself is unaffected. The best algorithms to solve the actual isogeny path problem is still the same today as it was a year ago. SIDH, SKI sign is unaffected. So SKI sign is a digital signature scheme. It is interesting in that it has the most compact public key and signatures of all post-quantum schemes that I know about. Research on SKI sign is still very well unalived. It's been submitted to the NIST post-quantum signature call earlier this year, and there's still a lot of activity around it. C-side has survived. It is unaffected for the moment. The algorithms, the best algorithms we have to break, C-side are still the same. This is a key exchange, extremely similar to Diffie-Hellman. You replace exponentiation in a group, in Diffie-Hellman, by a group action that comes from a class group of a quadratic field acting on some collection of elliptic curves, and this action arises from computing isogenies. And with C-side, a wide variety of C-side-inspired constructions have survived. You can think of it as a group action cryptography. Crypto systems you can build if you are given a group action that is hard to invert. So this means you have signatures, you have PRFs, you have a bunch of threshold stuff and oblivious stuff, many things. OK, I've gone through what died, what survived. Is there any hope of fixing SIDH? We can look at how the attack works and see if we can maybe amend the protocol. The attack works like that. You need to have the degree D, a basis PQ, and the images of the basis, phi of P and phi of Q, and then your secret isogeny is not secret anymore. You could try to hide some of this. Maybe instead of using a fixed degree D, in the protocol I presented, we use D a power of 2 or D a power of 3. Instead of doing that, we could randomize it. You use a random secret degree, and that leads to a proposal called masked degree SIDH. Otherwise, you could also try and hide a bit better the images of the points. Phi of P and phi of Q, you could replace them by A times phi of P and A times phi of Q for a random secret integer A. Why are you allowed to do that? Well, think about it. What are we using these points for in the protocol? Alice is using these points that Bob sent her to compute the image of her subgroup. But a subgroup is invariant under multiplication by a scalar. If you replace all the group elements by A times the group element, it's still the same subgroup. So she could just use A times phi P and A times phi Q as if they were the correct images, and she would recover her group up to a scalar, which is just the same group. And that leads to a proposal called masked SIDH. So these two were proposed and analyzed by Forza, Moria, and Petit at Eurocrypt 2023. And the main message for the moment is that, well, yeah, it kind of works, but the cost is huge. Just look at the size of the public keys. You had fairly small public keys in Psych. 197 bytes for the first security level, and that brings it up to more than 4,000 bytes, and that's not even talking about the computational cost. Okay, so that's just looking in the past. What survived, what died, is there any hope of fixing anything? But there's something much more interesting happening. The foundations of the field are changing thanks to the attack. To see that, let's talk a little bit more about representing isogenies. What have I said about the isogeny problem? I've presented an idealized version first. You're given two elliptic curves, can you find an isogeny between them? And then I concretized this problem by presenting the L-isogeny path problem. You're given two curves, can you find an L-isogeny path between them? All that is doing is giving a concrete meaning to what it means to find an isogeny. And for that, the L-isogeny path problem has become the standard meaning of the isogeny problem, simply because we have had no other interesting way to represent isogenies. How else would you represent a solution of that problem? So some technical obstacle led to defining this problem, L-isogeny path, which has a strong restriction. You're not finding any isogeny. It has to be a chain of isogenies of degree L. Maybe you can loosen this a little bit and replace L by a collection of small primes, and you're allowed to use all of these. But, well, still, it would be a restriction. So let's ask again. How can one represent an isogeny? An isogeny is a map from a curve to another one. So all you want is for an efficient representation of an isogeny to mean an algorithm that allows you to evaluate this map. An efficient representation of phi would just be some data about phi that allows you to compute phi of p for any input p. We've seen a few examples. Isogenies of small degree are efficiently represented in that sense by their kernel. Then you can use these small degree isogenies and build a more complicated one by compositions, building isogeny paths. You can do even fancier things. If they have the same source and target, you can take linear combinations of isogenies. But still, it always boils down to using very small degree isogenies and using them to build more complicated stuff. We're still stuck with these small degree isogenies. But let's have another look at the main result of the attacks. It's an interpolation result that says if you know the isogeny phi on a few points, then you know the isogeny phi everywhere. So this tuple, d, p, q, phi of p, phi of q, is an efficient representation of an isogeny. It is enough data to evaluate your isogeny on any input. This is something we can call the interpolation representation, or it's been called the HD representation. For instance, in some applications, key sign HD, the HD here stands for high dimension. Because of the way this works internally, I'm going to say a few words about that later. And what's extremely nice about this representation is that it is universal. By that I mean, if you have any efficient representation of an isogeny, you can immediately convert it into an interpolation representation. Because all you need for your interpolation representation is a few evaluations of your isogeny, and this is what an efficient representation gives you anyway. So it's universal. And you could try and use that to define a universal variant of the isogeny problem. Defined as follows: you're given two elliptic curves, E1 and E2. Can you find an isogeny between them, given in interpolation representation? So that defines a new variant of the isogeny problem, maybe the more universal variant, maybe the more natural variant. And you may be concerned, have we made the problem easier? It's possible, right? Because the L-isogeny path problem was asking you to find not any isogeny, but an isogeny that has strong structure. It must be an L-isogeny path. And here it's saying, well, okay, any isogeny will do. It's probably easier. So the good side of that is that, of course, it's more natural. You don't have artificial restrictions on the isogeny you're asking for. And also, it turns out that it is equivalent. The universal isogeny problem is equivalent to the L-isogeny problem. This is a paper that is not out yet. It's a work in progress with Aurel Page, which I hope will appear soon. One direction is very easy, because if you have an L-isogeny path, you can easily convert it to an interpolation representation. The other direction is much trickier. Now, this gives us a powerful new tool. this interpolation representation, maybe we can use it to build constructions. And indeed, we're already seeing new constructions emerging from this technique that was introduced in the attacks. The first one I want to mention is SkiSign HD, which is a variant of SkiSign. It's another signature scheme that is very closely inspired by SkiSign. It solves a bunch of problems we had with SkiSign. The main issue with SkiSign, well, I guess there are two big issues with SkiSign. Signing is kind of slow. It's of the order of a second. But mostly, it's extremely complicated. If any of you had a look at the implementation of SkiSign, there are many components playing with one another, a lot of mathematical abstraction. You have quaternions, you have isogenies, you have conversions between ideals and isogenies. It's very complex. SkiSign HD makes signing simpler. It makes it faster and simpler. And also, it improves the security proof. In SkiSign, part of the security proof is a little bit ad hoc. And in SkiSign HD, we get much closer to a standard reduction to a standard problem. Of course, there's a downside, which is that we're making constructive use of this method here. How efficient is it? Well, the problem is we're going to need to do this in the verification steps. So now suddenly the verification gets a little bit more complicated. But to know how complicated, we're going to need to dig into what this method actually does. Before that, I want to mention another application, FISTA, for fast encryption from supersingular torsion attacks by Basomeno and Pope, where they also do take this method and apply it constructively to build this time a public key encryption scheme. And the same concern arises. Now it's making constructive use of an algorithm that was introduced as an attack. And it says it's fast. So really, how fast is it? As the authors put it, the fast in the name is inspirational. It's not quite as fast as we would hope yet, but I'm very curious to see where this is going. So as I said, constructive use of an attack, it doesn't mean the same thing for an attack to be efficient as it does for a construction to be efficient. Construction, you want it to run in, I don't know, maybe milliseconds will be good. An attack, well, if it runs in a year, it could still be a very valid attack. So let's see how it works. I'm going to need to talk a little bit about isogenies in a higher dimension, but I hope I've abstracted away most of the difficulties so that if you're not familiar with abelian varieties, it's still going to be fine. But before that, I need to talk about a notion called the dual. It's also a very elementary notion in the theory of isogenies, but I haven't talked about it yet. So here we go. Consider an isogeny E and an integer n. Multiplication by n is the map that sends a point to n times the point, so p plus p plus p plus p plus p. It is itself an isogeny. It's an isogeny from the curve to itself, from E to E. It's what we call an endomorphism. Now consider an isogeny, an actual isogeny between two different, possibly different curves, E1 and E2. The dual of this isogeny is the unique map that goes in the reverse direction, such that if you compose phi with its dual, what you get is multiplication by the degree. So what's interesting about the dual is that it goes in the other direction, and it has the same degree. And it's really defined like that. It's the unique one, so that phi composed with phi hat is multiplication. OK. Now abelian varieties. What is an abelian variety? Well, the simplest example of an abelian variety is just an elliptic curve. In fact, an elliptic curve can be defined abstractly as an abelian variety of dimension 1. It just means that it's a curve, dimension 1, that is also a group, abelian variety. But you could look at things in higher dimension. And instead of looking at curves, you could look at surfaces, and you'd call that an abelian surface. It's just a surface that is also a group. And maybe the simplest example of that would be the product of two curves. A product of two elliptic curves has dimension 2, because each elliptic curve has dimension 1, and it's still a group, because the product of groups is a group. This is an abelian surface, E1 times E2. Now, of course, you could keep going higher in dimension, and then you don't have a specific name for every dimension, but in general, you call that an abelian variety. And if you have n elliptic curves and you take their product, you construct an n-dimensional abelian variety. Of course, not every abelian variety is a product of elliptic curves. But all the abelian varieties that I'm going to talk about today are products of elliptic curves, so this is enough for you to understand the rest of the attack. Now that we've defined a higher dimensional analog of elliptic curves, let's see what's happening with isogenies between these. An isogeny would still be just a map between two such abelian varieties. So let's look at the two-dimensional case and product of elliptic curves. So you have two products of elliptic curves, E1 times E2 and F1 times E2. We're looking at isogenies between them. How could you construct isogenies between such products? Well, you're given a pair of points as inputs, and you're asking what pair of points can you get as an output. And maybe if you have one-dimensional isogenies between some of these components, you could build such a map. And indeed, if you have an isogeny phi11 that goes from E1 to F1, you could send P1, P2 to phi11 of P1, and then something else for the other component. If you have another isogeny, but that goes from the second component, E2, still to F1, you could add them together. And now if you have other isogenies that go to F2 instead of F1, you could have them here. So a fairly straightforward construction. This may look a little bit messy written like that, but if I put it in matrix form, what I get is that, and it's a little bit nicer. It's really some standard matrix vector multiplication that gives you this formula, where instead of whatever numbers here, you would have isogenies in your matrix and points in your vector. What I claim is that any isogeny between two such surfaces is of this form. Whichever isogeny you have between two products of elliptic curves, it always actually is a matrix of one-dimensional isogenies. Some of these are more interesting than others. The interesting ones are the ones we're actually going to be able to compute, and we call them n isogenies. N is an integer, and an isogeny like that is called an n isogeny if when you take its matrix and you multiply it by what I'm going to call its conjugate transpose, then you get the scalar matrix of multiplication by n. I'm calling it the conjugate transpose because, well, as you can see, I've exchanged the terms of the antidiagonal, and I've dualized everything. So it's, if the dual corresponds to the conjugate, this is what you'd get. So the matrix times its conjugate transpose is scalar multiplication by n. If you have that, you call that an n isogeny. And these are the good ones, the special ones, the ones you can compute, at least when n is smooth, when you don't have any large prime factor in n. The most favorable case is when you have a 2 to the n isogeny, then you can compute it in polynomial time. OK, why am I saying that? We were talking about isogenies in dimension 1, and suddenly we go up in dimension. What do we gain? Well, from this result here, that any isogeny in dimension 2 decomposes as one-dimensional things, maybe we can hope to learn something about one-dimensional isogenies by looking at such isogenies. Maybe one of these components here will be our secret isogeny, and for some magic reason, we are able to evaluate the large degree thing without evaluating each individual component of the matrix. Is that the case? Well, let's see. Consider an isogeny phi from E1 to E2 of degree 3 to the m. That would be Bob's secret. And for the moment, to simplify everything, but I'm going to lift this restriction soon, I'm going to suppose that 2 to the n minus 3 to the m is a square. It's equal to a squared. Now, we can define an isogeny from E1 times E2 to itself, to E1 times E2 again. And we can define it like that, by this little matrix here, where on the diagonal I have multiplication by a. A is an integer. And on the antidiagonal, I have phi and minus phi hat. Why is that interesting? Well, the first reason to think that could be interesting is because you have your secret isogeny here. And if you can evaluate this isogeny psi, the large one, then you have an algorithm to evaluate phi also. How so? Well, just look at this composition of maps. You start with a point P1 on E1. You include it into the product, so you would get the pair P1, 0. Now you apply psi, and this is just a matrix vector multiplication. And just looking at this matrix, you would get to AP1 and phi of P1. Phi of P1 is indeed in the second component E2. And then you project to the second component, you get phi of P1. So this says if you can evaluate this map in the middle, this big psi, then you can evaluate phi, which is Bob's secret. That sounds, it sounds a little bit too much like a triviality, right? I've constructed this big, complicated isogeny in higher dimensions by putting my secret in there, and now I say, if I can evaluate the complicated thing, then I can evaluate the simple thing. Well, sure, yeah, okay. And it looks like if you want to evaluate it anyway, you need to evaluate phi, right? Because to do this step, I'm taking P1, and the second component is phi of P1, so I just need to evaluate phi there. But maybe we have another way to evaluate psi. As I said, if psi turned out to be a 2 to the n isogeny, and we knew its kernel, then we could evaluate it efficiently without going through this matrix form. So is it the case? You may suspect that it is the case indeed, but let's check. We can do the computation. To check if it's a 2 to the n isogeny, we take the matrix, we multiply it by its conjugate transpose, and you can easily figure out that it gives you this matrix here, where you get the a squared by multiplying a, and you get the 3 to the m by multiplying phi by phi dual, simply because 3 to the m is the degree of phi. And a squared plus 3 to the m is just 2 to the n by this equation here. So it is indeed a 2 to the n isogeny. OK. Now maybe I can evaluate it if I know its kernel. But do I know its kernel? Formally, I know it. I can write it down. Mathematically, it's this. The kernel of psi is the collection of all pairs of this form. I take p in the 2 to the n torsion of E1, and I'm looking at all the pairs of the form 3 to the m times p and a times phi of p. These pairs, they are in the kernel of psi, and they are in fact all that is in the kernel of psi. So I know the kernel. But, well, do I? Because to compute the kernel, it looks again like I need to evaluate phi. I need to compute this phi of p here. Well, sure, but I don't need phi of p for any p. I just need phi of p for p in the 2 to the n torsion. Aha, and now we have the attack. Because Bob is giving to Alice the evaluation of his secret on the 2 to the n torsion, which is just what she needs to compute this, so the kernel of psi. So from leaking phi on the 2 to the n torsion, so that's the torsion point information leaked in SIDH, we can compute the kernel of the 2-dimensional isogeny, which means we can evaluate the 1-dimensional isogeny phi. And we're done. This is the attack. Well, this is 90% of the attack. There's this little problem here that we need to assume 2 to the n minus 3 to the m is a square. 2 to the n minus 3 to the m is a very large integer. What are the odds that it's a square? Well, if it behaves like a random integer, pretty much 0. What if it's not? Well, if it's not, that's where Robert comes in. Robert has a solution. He has a solution first in the case where it's a sum of 2 squares. And you may know that sums of 2 squares are much, much more common than squares among large integers. So what would you do if you have a sum of 2 squares? You could do the very same thing with a slightly more complicated matrix. Now you need to work not between abelian surfaces, so 2-dimensional things, but between 4-dimensional abelian varieties. So you define a map from E1 times E1 times E2 times E2 to itself, and it's defined like that. And the matrix, you may notice, has a very similar structure. It's mostly 4 blocks, where on the anti-diagonal you have phi times the identity, and here you have minus phi hat times the identity. And what's a little bit more complicated is happening on the diagonal blocks. But with the very same reasoning, you can realize that this is a 2 to the n isogeny, and you can compute its kernel, so you can evaluate it and run the very same attack. But now what you need is not an isogeny in dimension 2. You don't need to evaluate an isogeny in dimension 2. You need to evaluate an isogeny in dimension 4, and that is a fair bit costlier. And still, you're not done because, sure, sums of two squares are much more common than squares, but they are not all integers. What can we say about all integers? Well, then Robert has another solution, inspired by what's known in the study of abelian varieties as Zarin's trick, which starts from the observation that any integer is a sum of four squares. That's a very old theorem, maybe Legendre, I guess. And Zarin's trick tells you that you can construct endomorphisms in four-dimensional abelian varieties that have a very special form, and you get to, you can see it coming, a more complicated matrix that still has the same general structure. You still have mostly four blocks with phi times the identity and minus phi times, minus dual of phi times the identity on the anti-diagonal. And this is again a 2 to the n isogeny, you know its kernel, and you can evaluate it. But now that costs you the evaluation of an isogeny in dimension 8, that is even costlier. Now, how costly, and is that a problem for constructions? Because if you want to use these algorithms constructively, it means you're going to have to evaluate high-dimension isogenies. So let's see. First with FISTA, this fast encryption from supersingular torsion attacks. It's using the attack for decryption. And here they managed to build the scheme in a way that only the two-dimensional case occurs. The two-dimensional case is the first case I presented to you, the one where I was assuming that 2 to the n minus 3 to the m is a square, and they restrict to this case. They don't actually, they go a little bit farther. They don't have that 2 to the n minus 3 to the m is a square. You can apply a little bit more tricks to increase the range of applicability of that technique, but still, they only use two-dimensional isogenies, and that is very good because they are well studied. Two-dimensional isogenies of degree 2 even have a name of their own. We call them Richelieu isogenies. They are fairly efficient. We have good implementations available. Now, SkiSign HT, this signature scheme inspired by SkiSign, we need to run the attack for verification. And this is where the scheme hurts a little bit because you need four-dimensional isogenies. And four-dimensional isogenies, they are not well studied. What the literature tells you is essentially, oh, it can be done in polynomial time. And you have no good implementation available. And what polynomial time means here is probably a fairly big polynomial. But you could put that on the account that only one person in the world has been studying this problem, and well, now there's more workforce joining him. So there's a lot of activity around this problem of evaluating isogenies in dimension 4 at the moment. People are working on new techniques, new implementations. Some back-of-the-envelope computation suggests that it may become quite practical. I'm not sure what practical means yet, but we hope that it's going to be practical enough for a verification of a signature. And that concludes my talk. Thank you for your attention.
Thank you, Benjamin. We have a few minutes for questions if anyone has any. There's some microphones if you do have a question. Maybe while we're waiting, I'll just ask, so SkiSign was submitted to the on-ramp. Was SkiSign HD not submitted, just it's too new, still ongoing research, or?
Oh yeah, well, SkiSign was not ready by the deadline. SkiSign, I think we made the result public, what, in February or something like this. We still don't have an implementation for the verification, precisely for that reason, that the verification needs four-dimensional isogenies, and the literature is just not there yet.
Okay, got a question? Someone's coming real quick. Just one sec, I think someone's coming to fix it. That way online we'll be able to hear as well.
Hello? Yeah. My question is just, you still need a smooth degree of the isogeny, or can you compute any isogeny if you have the points now?
if you have the points, any isogeny would do. All you need is that you would have the degree of your secret isogeny minus, or what is it? No, a large power of 2 minus the degree of your isogeny would be something, what is it? No, you don't even have any restriction in the 8-dimensional case. In the 8-dimensional case, you could just have any degree isogeny. If you have its evaluations at enough points, then you have the isogeny.
We got another question here.
Question is, as you have introduced that C-side has many C-side inspired construction, and I want to know if there are some possibilities to applying SkiSci or SkiSci HD to some high functionality scheme.
I didn't hear the question very well. Can you repeat?
Can you get a little closer to the mic and be a little louder?
My question is it possible to applying SkiSci or SkiSci HD to construct other high functionality primitivity?
Oh, okay. So instead of building signatures, building more advanced crypto systems. Is that what you call higher functionality? Or? I think that the mic is off again, or is that me?
We'll just switch to another mic, perhaps. So you're saying from C side, it's easier to construct more advanced functionalities?
Yeah. Sorry.
Perhaps we'll let you talk in the break. We have one more question here.
Yeah. First of all, thank you for the very nice presentation. From my understanding, N and M are public anyway. So, what is the need for AD isogenies if we can just, like you said, for the 4D isogenies, for most of the integers N and M, there will be like 2 to the N minus 3 to the M will be a sum of 2 squares. So can't we just like choose them, standardize them, and then just use this and stick to 4D isogenies?
Well, it depends on your application, right? If in your application you have some freedom in your choice of the degrees that are involved, then sure, you would want to make the most favorable choice for you. Finding parameters so that the difference would be a square sounds totally infeasible, just because squares are way too rare. But so to make them sums of 2 squares is very feasible. But in some applications, maybe you have no choice in the numbers that are involved. So then you would need the 8-dimensional case. And in SkiSci HD, here I'm saying we need 4-dimensional isogenies. That is in the more favorable case of SkiSci HD, where we need some heuristics here and there to say that all our numbers are going to be well represented, that we're going to find a sum of 2 squares. But if we want a fully provable version of SkiSci HD, we need the 8-dimensional case.
Okay. Let's thank Benjamin again for a nice talk on isogenies.